Right, so today I wanted to walk you through an introduction to analog system Verilog. And let's dive in. So, what's this all about? I'll try to give you context and why we need to think about this. And then you introduce a couple of concepts, look at some code for what I mean by analog system Verilog. So first of all, what I've tried to do here is to illustrate sort of the full development process for a chip. Now, today, a lot of the things that we do requires both analog and digital. And it sort of makes sense when digital is dense and analog is still hard to make, to do a lot in the digital world of Verilog and automatic layout and sort of the full RTL to GDS flow of OpenRoad, for example. But when we start with an idea, and maybe this is a bit small, but I'll try to point it out. Maybe we should go full screen. That's a bit better. So we start with the idea of what we want to make, and then we break it down into analog parts and digital parts. Now for the analog, we do the design in XGAM, and here I'm only talking about the open source tools. We'll do the analog simulation in ngSpice, and then when we're happy with the design and think that this will probably work, we do the analog layout in Magic, and then we do the layout versus schematic in NetGAN, and then we'll extract the capacitance and resistance from the actual layout and then resimulate over corners. So process, voltage, technology, temperature, and make sure that the design as we think it should work probably will when we get it back from the foundry. For the digital design, it follows not a very different flow, but very different tools. So we write the digital design in SystemVerilog. If you're starting digital design today and you want to make chips, I'll just say do the SystemVerilog. Just use that, forget about everything else. Somebody may have different opinions, but that's mine. You'll simulate in a digital simulator, which could be iVerilog, and I think iVerilog and VPP is actually two sides of the same coin. iVerilog, I think, is the compiler, and VPP is actually the thing that runs through the simulation. And if you want to include software or anything large, you probably want to do Verilator, which I haven't used it myself, but I believe that's sort of a faster compiled digital simulation. And you'll look at the waveforms in GTK Wave, and you'll make sure that the digital functions that you make actually does what you think they should do. And you might run the RTL to GDS2 flow in OpenRoad. Now inside this RTL to GDS2, it is actually quite a similar flow to the analog. It'll do first it'll do synthesis, so translate the registry transfer level netlist to actual gates like flip-flops and NAND, NORs, whatever. And you'll have to also do timing analysis on that netlist to make sure that between the registers, the data arrives at the right time compared to the clock, not too early, not too late, and so on. And you'll have to do clock tree synthesis, you'll do place and route, and you'll do all the things to make sure that the digital layout actually corresponds to what you think it should be based on the RTL. Now, most of that, I believe, is quite hidden in the OpenRoad, and that's sort of designed to be an automated way to generate digital hard macros, or GDS2s, that you could actually tape out. But if you want to combine analog and digital, then you sort of have to meet at some point. And in the end, maybe you use the GDS2 from the analog layout, and you include that into the RTL to GDS2 flow in OpenRoad. But when you start to design your digital, you somehow have to know how the analog is supposed to work quite often this is actually two different people, right? So you have a digital designer or a digital design group, and you have an analog designer or an analog design group. And they don't necessarily speak the same language, but they have to communicate somehow. Design intent and how the analog module is going to work, that has to be communicated. And the point I want to make today is that when you're making complex systems, which will be digital on top, then it makes sense to make a behavioral or functional or sort of a model of how the analog system works, but make it in a digital simulator. And let me try and explain why. So digital simulation. Actually, it's a good training exercise if you have sufficient amount of time to make your own digital simulator. It is not that hard. Because in a digital simulation, most of them are based on sort of what we call event-based simulation. When something happens, compute what happens next. And the good thing about digital simulations is that they're causal. So the order of execution at a particular event doesn't really affect the past. So you can't have a signal at an event, a certain point, affect things in the past. That doesn't happen. And I've tried to reuse an old flowchart here on the left side. So we start, and then we say, okay, let's jump to the next time step. The units of time here actually don't matter in the digital simulation, unless you want to compare the real world, but it's sort of just a concept of now we're at a certain point in time. Call it 1, 2, 3, 4, the real numbers. And then at that timestamp, you check, is there anything that's supposed to change right now? And if there is, then you take that event away and you execute it. And once you execute it, it will always schedule an event in the future. So you won't recompute on the same time step, sort of multiple things. They will also always be slightly into the future. It doesn't have to be nanoseconds or microseconds. It can be sort of virtual time. So like, we shouldn't think about time units here as in seconds. We should think about things that happen next in the flow. So I set a signal to 1, but I don't apply it right now. It happens in the future. Because if something is looking at that signal, well, that should also happen in the future. Once you've done all the events in that particular time, you find the next time step. Now, it could be that before you executed a particular event, your next event was, let's find the camera. Sorry. You have an event here, and you're going to here. And then after executing this event, you actually insert a few new events because things happen closer in time. Imagine you have a clock driving a combinatorial logic. If the clock actually, or not a clock, but the output from a flip-flop driving combinatorial logic, that will usually happen faster than the clock. So once you've computed an event, then you can know what the next time step is. And then you just go around in a circle until either you stop or there's nothing more to compute. So fundamentally, digital simulation is very different than analog. I like to think about it like, I think I used an analogy once. So think about a grand old man who knows when everything is supposed to happen. He's looking at everything that happens and then schedules what you should look at next. And that's kind of like what happens in the digital simulators. You have a event queue, so 30 nanoseconds. You might actually have roughly the same time, because the time unit is not important, but you have an event at 30, you have an event at 30, but it's actually slightly later, or a delta time later, and then 21, and so on. Now, in this list of events, obviously, you would pick the 10 nanosecond first, and you run that event. And that will insert new events into your queue. Now, I actually made a digital simulator once during my PhD. I don't think anybody else has used it, but it was a fun exercise to sort of get to the concept of event-driven simulation. And I made it in C# because at that time I had a deep love for C#, which I still have, but I since then switched to Mac and Linux, and when I switched back in 2006, Mono and .NET, the new one, the 7, wasn't really there, so I sort of left C# for a while. But anyway, I made a simulator that time, and then made the type of event queue where you can insert things. And that's basically how things work in a digital simulator. And if you want to buy a commercial one, you have, I think there's mainly 3. You have Cadence, Siemens Mentor, and Synopsys. That's the big 3 EDA companies. And they're expensive tools, and they can do a lot, and they're really good. There are also open source ones, like Verilog. I don't think Verilator is an open source one. And then, of course, mine, which I wouldn't necessarily recommend, but if you want to learn how to make an event-driven simulator, then it could work. I think I last updated that back in 2005, so anyway. So, digital simulators, they only compute what is necessary. And they don't do anything extra, which means they're fantastically fast. Now, compare that to analog, it's very, very different. Let's switch the slide. Oh, crap. Let's wait while my... There we go. Oh, too far. No, not too far. Actually, let's go through an example. So what I have here in the code is a counter. So we have split up the counter into always FF, so synchronous logic, which will turn into flip-flops, and we have always comp. I would recommend that if you're writing Verilog, that's the 2 constructs you use, always comp and always FF. That'll help you to think right, because anything that's in always comp should be combinatorial, anything that's in always FF should be synchronous type of flip-flops. And if you use any of the old constructs in Verilog, like always, you don't really know what the code will... Well, you have to write the code in the right manner to get the right type of logic. But when you use always FF and always comp, then SystemVerilog and the compiler will help you ensure that you end up with combinatorial for the always comp and synchronous for always FF. So let's start with the always FF part. We have 2 signals coming in, clock or a reset. And if we're resetting, so this is an asynchronous reset, then we reset the output signal. Or else we set the output signal to the count. Okay. Now, if we look at the combinatorial, then in this case, it will always look at the out and it'll add 1. So at the input to the flip-flops in the always FF, the count will always be set after a certain time, the time delay of the combinatorial, and then as soon as we set the out, then a new set of values will ripple through the combinatorial logic. So if we think about how this will work in a digital simulator, then let's just assume all the inputs and outputs are 0. When we get an event, so we look in our event queue and we find that the clock, that goes to 1. Okay, then we compute what's supposed to happen next time. And the first thing that should happen is that we set the out variable to count in the next event. Now, that might be quite fast, or we might actually model the delay of the D flip-flop. So this is where timing can come in. You can either add that timing to the Verilog, or you can use a Liberty file to describe that timing. Once you have the outset, then there will be a bunch of sort of delta events, small events, because now we're rippling through the combinatorial logic, and it'll take some time, or a number of events, before the count variable is actually correct. And here it might ripple through different type of states, but at certain point, the count, which is a certain, well, in this case, it's 8-bit wide, the value of that count will be correct. And then nothing more happens until we get the next pos edge or the reset signal. So that means in a digital simulator, you sort of have to keep track of the always FF type of things. What do they depend on? and you have to keep track of all the gates, and you have to know what type of signals they depend on, but you don't need to search through all of them. Because as soon as you're supposed to do something in the future, you add it to the event queue, and when the event queue, or when the run compile, or when you're computing what happened at that event or that time step, then it does something. Now, of course, as I said, from the out variable set to actually count changes, it will be some time, or a number of events. And if we look at the synthesize code, well, this is an 8-bit counter, so we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 flip-flops, which is what we would expect. So that's sort of the always FF section. And then we have a set of combinatorial logic with ANDs and XORs and sort of the normal adder tree for our combinatorial logic. So that means, for example, as soon as we set a bit out here, as soon as that bit changes, that will ripple back and events will be added into the queue. For example, here for, let's see, I think this is bit 2. Well, then we have to add an event to the queue where the Y output of the AND changes. And then it ripples through. And then now this is, at the RTL level, it might have some sense of what happens when. Maybe there's some delay in the AND in the Verilog, or maybe not. So an important part of the timing step is to actually add real timing. So then we've used spice simulators to actually compute how long does it take from A input of the AND changes to the Y output changes. And we store that in the Liberty file. And then also after layout, we have to introduce parasitic, both resistance and capacitance, mostly capacitance though, to modify those delays, which means that also in digital we need to do netlist simulation, or simulation at the level of the actual design to see that it still works. But then you're getting into a situation where it could actually be quite a lot of stuff that changes, and there's a lot of components in there. So it's also possible to, in digital, run what's called a static timing analysis. So since you know all the delays, you can find the critical paths and you can prove that the delay of the full adder tree is short enough for the count variable to be correct before the next clock strikes. And it's actually important also that the count variable is held long enough after the clock strikes so that the D flip-flops, or what we call the hold time, the D flip-flops don't change value because the data changes right at the clocks, for example. But all of this is pretty quick. I mean, we can do millions, billions of gates. Maybe not billions of gates. Well, at least millions, hundreds of millions of gates on an integrated circuit. And we actually simulate that in hours, days. Now, analog simulation is fundamentally different, because what we're trying to do then is, for transient analog simulation, we are reading in a netlist, we're figuring out the partial differential equations for all the nodes in the system, and we will have a nonlinear model of voltages, currents, maybe even charge, and sort of what we want to compute is, given a set of initial conditions for the full matrix of all the nodes and all the sort of matrix transformations from the outputs or the nodes in the network to the next value, which is a function of the current state, or sorry, the current state, the previous state, the derivative, the second derivative, the nth derivative, and this becomes sort of a Taylor series expansion, where you describe a function based on the sum of a coefficient times the derivative. This becomes a huge sort of matrix that you have to compute. Now, we can't do this closed form. You can't sort of write the single line of code that does this. You actually have to use numerical methods to compute the next value. And here it can actually be non-causal also, because sometimes maybe you have to step back in time. It depends on whether you do forward Euler or backward Euler or other numerical methods to be able to compute the derivatives and the current states and the integrals and just a simple thing as computing the current that goes into a capacitor. So we know that I equals C times dV, so derivative of voltage divided by time. Or, yeah, I equals C dV dt. So in that case, we actually have to integrate the voltage change times the capacitance to find the current. Was that correct? Yes, it was. Now this is tricky, and this takes time, which is why transient simulation takes time, and especially when you have parasitics, resistance, because then you have a bunch of nodes in your system, millions of nodes. So analog simulation is fundamentally slow. Now, SPICE, which is the program that originated, well, where all the simulators today started, 1973, a simulation program with integrated circuit emphasis. And you can go and read the original paper for SPICE. ngSPICE is based on, I think, SPICE 3 from Berkeley. So it's pretty old sort of core of how to compute these differential equations using, I'm not sure what it uses actually. I haven't looked in the code. You can go and look at that if you're interested in numerical methods. But for SPICE simulation, you also have commercial tools. I would say that for analog design, then Cadence Spectre is dominant, but also Eldo was pretty good. You have fast SPICEs like AFS and what's it called? Maybe it's not called Berkeley SPICE still. Well, at certain points in time, there will be faster SPICE engines. And what they're actually trying to do is, one of the key things when you're trying to figure out the next state in this horrible equation of nodes is how long time step can you take, because the time step that you take to compute the next value actually depends on the derivatives of change in voltage and current and all that stuff. So some simulators try to be a bit more creative, which is why we get fast SPICE, but anyway, all of them are slow. It's common for an ADC, for example, to have run times for a transient simulation where you're trying to get an FFT or trying to figure out the signal to noise and distortion ratio for the ADC. That can run for days or weeks. We have also a few free tools. There's one called AimSpice, made at NTNU by Trond Ytterdal. And we have Analog Devices LTSpice. And then you have the open source ones. So here I know of ngSpice. I think also there's also one from Sandia National Labs. I don't know if that's open source, but maybe it is, called SICE. I haven't used it yet, but that's supposed to be sort of a made for massively parallel systems and supercomputers. So it'll be great when that actually works with Skywater. Okay. So now you have some concept of analog simulation, what we have to do there for transient, so to compute the time evolution, and you have some concept of what happens in a digital simulator. Now, imagine you have a big system with what we call big D little a, or a lot of digital and some analog. It may be a power system, it may be a PLL, it may be a ADC, it may be a temperature sensor, all the stuff that just has to be made in an analog world and simulated with an analog simulator that has the device physics included. If you want to combine those two, then what you actually have to do is orchestrate the events and the time steps in the transient simulation in the analog, such that things happen at roughly the same cadence. And then you have to insert digital to analog converters from the digital side to the analog side, and ADCs for the signals going back. Now, what actually happens in this type of system is that almost always the digital simulator will sit there and wait for the analog simulator to compute something. So the analog simulator is the slowest part here. Digital will always be faster. And at a certain complexity level, like an ADC with a digital part, this works fine. It is a good way to verify that for example, for a sigma delta, your decimation filter works well with your ADC. However, when you go up to chip level and you have maybe 50 analog IPs and you have hundreds of millions of gates, it breaks down. You can't do anything because it's too slow. It doesn't work anymore. So then we have to have something different. If we actually want to verify some of the behavior, not all of it, but some of the behavior at the top level, so the digital, then we have to do something different. So imagine, for example, we take the temperature sensor that you've been working on, and you just want to verify that you've hooked up these signals correctly. The one to turn it on, and the one to read out the digital value. And you just want to make sure that you hooked it up correctly, that you do the right thing in the digital design. For that type of check, you don't actually need the temperature to be correct. It doesn't need to be a perfect simulation, because all you want to check is that the interface between the analog and the digital, you haven't made any simple mistakes or any sort of screw-ups there. So then what we do is we get to the analog system Verilog. And here I'm going to step back in time a bit. A few years ago, well, some of you I think had this course, but I had a project in a course, Design of Integrated Circuits, where I told the students to model this was an image sensor, which has a photosensor and a comparator and an 8-bit memory. And in this case, we have a mix of analog and digital. I think maybe when I gave this project in the third year, I overestimated or underestimated how complex it would be for that point in time. But it might be easier to understand now. So we made the analog circuits in SPICE and the digital circuits in SystemVerilog. Now, just a quick recap of what this was. This refers to a paper. You can actually find the link to the paper here of a cool CMOS sensor. A very high speed one, 1,000 frames per second. 10,000 frames per second. And the way they did that was to integrate an ADC into every single pixel. So the way that the image sensor works is that you have a photo gate that can collect light and convert light or the photons hitting the silicon lattice, generates electron hole pairs. You ensure that you have some field in the well region that collects photons such that you separate the electron hole pairs and you sort of collect the electrons. At certain time then, you will transfer the charge or transfer the electrons to a small capacitor, maybe a femtofarad, and that will change the voltage. Then you run a ramp, so that's illustrated here. I think, let's see, do we have an exposed signal? No, we don't have the exposed signal here, but once we've exposed the pixel, we collected the electrons, then we run an analog ramp going into the comparator here, and we synchronize that to a digital ramp going to 8-bit memory in every single pixel. This is kind of like, imagine you have, I don't remember how many pixel there was in this case. Let's check that. So it seems to be, yeah, I can't compute that right now, but a bunch of pixels. Let's say 1,000. You can do all the 1,000 pixels in parallel because you feed in a ramp that is the same to all pixels, and then you feed in a digital ramp with a digital signal that is in sync with the analog ramp, and then every single pixel will just determine when the voltage on its capacitor is equal to the ramp and then lock the memory. So you do sort of parallel locking or conversion of the whole pixel array. This was a kind of cool paper when it came out. I really like this. So then we have a system with a SPICE core, where we have a sensor, we have a comparator, and we have a memory. And then we have a SystemVerilog, a digital part that's supposed to read out all the pixels. Now, when we make the SystemVerilog, we kind of have to know how the pixel sensors work. And that's where I gave you a pixel sensor Verilog model. I don't think we really discussed what happened there, but you can go to this link and you can find under project. So this is DiceX on my repository. If you go to project, Verilog, and then you'll find the pixel sensor V. And let's go through what actually happens in this code. And let me try and make it bigger. So I added it in the slides also. So this Verilog module is not something that should be synthesized. It will be replaced with the GDS of our pixel, the analog pixel. But this Verilog model is supposed to emulate the behavior of the analog system. But notice that the first signal here, that's actually the bias voltage to the NMOS in the tail NMOS in the comparator. But that's a logic. So that has 4 states: 1, 0, high Z, and unknown X. And the same for the ramp. That's also logic. And then reset, well, that actually is a digital signal, 1 or 0. Same for erase, expose, and read. But in the real system, these two will actually be analog signals. So in SystemVerilog, a while ago, it wasn't possible to have wires have analog value. So you only had logic. These days, there's something called WReal, which can actually be wires, and where there is some functions in the simulators and compilers that understand what happens when two drivers are forcing a value onto the wire at the same time, WReal. I'm not using WReal in this example because I'm just emulating what happens on the VBN and ramp. But if you think back to the timing diagram, what we actually want to do in the timing diagram is to provide an analog value on the ramp. But that's not possible in a digital simulator. And the same for the VBN, we have to know what to do. But that's not possible either. But here is when we cheat. We fake it. Because it doesn't really matter that it's not physically correct. What we want to emulate is that the behavior is correct. So in SystemVerilog, you can use real values, which is, I guess, floating point. I don't know the precision or the standard, but it doesn't really matter. It's a real signal. And here I have a couple of parameters. I have the erase, and then I compute the least significant bit. And there's a delta voltage. I assume this is sort of just emulating the light current. A couple of temporary variables. And this is going to be my, that's the data coming in and in out. So the data is actually bidirectional, because as we're increasing the ramp, we are also synchronously feeding in a ramp in digital on this data signal. But then when we want to read out, we actually access this data and put that on a bus that is accessible and readable by the system. So the first thing we need to do is to actually erase the pixel. So when erase is high, then we set the temporary variable to v-erase. Easy. Right? That's the start voltage. And then what we want to do is the sensor itself, to expose it, we want to provide a way for the erase voltage to change when we expose. And by controlling the exposure time, we actually want a different value for the this temp variable. So that's the voltage on the capacitor we emulate. Now in this case, the way I chose to do it is actually to provide a clock, because we need something to be put into the event queue. And in this case, if we use a clock on the VBN, then I can emulate what happens every sort of single clock period. The clock is here not a digital clock. It's just something to make things happen. So if the we get a pulse edge on the VBN signal, which is in the real world, it's the bias signal to the NMOS. So this has no relation to the real world, but we're using this in a simulator to emulate what should happen. Now, the digital will not set a clock up here. That's something we just do in a test bench. So if we are supposed to expose, then we integrate. Well, I guess integrate is, well, it's fine. We integrate a negative value, so the temp value here decreases with time, which is what would happen in the pixel. The voltage on the pixel will decrease with time, depending on the exposure. Once we've exposed the pixel, then we want to run the ADC conversion. And the same thing here, we're not able to put in a real value. Well, you can, but I haven't done that in this example. Put in a real value on the ramp signal. What I'm actually just doing is feeding in a clock. And that clock using an internal counter. So I have an internal state variable called ADC. And that is incrementing every time we get a passage on the ramp. When the ADC value exceeds the exposed pixel value, then we set the comparator high, which is actually what happens inside the analog pixel. Let's make it slightly bigger. Now the memory, we just model that as combinatorial logic. When the comparator is not equal to 1, then we set the internal variable, the memory value, equal to the incoming data signal. So that means as soon as the comparator signal here goes high, then we stop. Then the data is locked inside the pixel. And then when we want to read it out, we actually change the data from being connected to, let's see. When we read, then we take the P data, or then when we not read, we actually have it high set so somebody else can drive the data signal. Now, what we've done now is create a model of how the analog parts work. And it's enough information for a designer of the digital part to actually make the digital part. And when you hook them together, then if you've done it correctly, then everything will work. So when I talk about analog SystemVerilog, it is you try and make a Verilog model that emulates the behavior of the analog SPICE model with sufficient degree of information so that you can do the digital design and you can verify that you hooked up the buses correctly. For example, we can check that if we check the analog Verilog model of the pixel versus the actual SPICE simulation, we can verify that the data is the right MSB to LSB order. However, if we then, somebody in the digital then had flipped the bus, for example, we would see that in the digital simulation and we can verify that that was wrong and we can fix it. So it's not a perfect way of doing it because you have this instance of you have a SPICE model of your system, you have an analog Verilog model of your system, and you have to ensure that those two are similar in behavior. But the extra complexity of doing it like that is worth it because you're able to simulate the top level of a chip in an efficient manner. And you can actually, for example, if you have communication between two chips, in the digital simulation, you can instantiate two versions of your chip and you can get them to talk to each other, which would be not possible in analog simulation. Okay, so I've included in the presentation the code that I just showed you also. I also have linked in a video from Synopsys, though this, I believe, is one of the guys that is working on the SystemVerilog analog standard, and he talks a bit about the real versus the W-real signals and how you can use them. And it's quite an in-depth discussion on peculiarities of modeling, but what I wanted to do today is give you an introduction to the concept and tell you that this is actually something that people work on. We have people that specialize on making digital models of analog systems, and they're good at that, and you can actually make a job out of this. So if you like programming, if you like analog, then this is quite interesting, because we do this because of simulation speeds. You can't run transient simulation on the top level of a full system on chip today. It's just too complex. You can do that for the simple things like a power management chip, but for a microcontroller with a Bluetooth radio and other types of radios, or any type of really complex systems with millions of gates and tens of analog IPs, you simply can't do it. And it might not be possible in the future either, because computers are not getting that much faster. So it is a necessary step to make digital models of analog systems. Okay, that's what I wanted to cover today. Have a good day.